This is a very quickly made up set of lectures for a Discord study group for quantum field theory, but I do hope it becomes more generally available and useful to perhaps anyone that's interested in the topic. This first set of notes is just a review of classical field theory, its geometry, and generally speaking how it works, what's the framework involved. So physics attempts to bridge spreadsheets and observation by means of equations of motion. So you have lots of tables of positions, velocities, momentum, masses, and energy, and you want to transform this table of observations that you've made into some kind of predictive mathematical model. Now, there are several types of methodologies in which we transform these tables into equations of motion, but the most useful sorts of methodologies are found in the field of mechanics, and specifically classical mechanics, where we really begin the journey of physics and where it never actually really ends. And mechanics has a very simple objective. If you have a configuration A and you have a configuration B, what's the path that took the point from configuration A to configuration B? Now, that sounds very abstract, but if you can imagine a very simple particle in space-time, so in this particular drawing we have a xa, ta, so a position xa and a time ta, and we have a point xb and a time tb, mechanics really can ask, how did we get here and where do we go from here? So if you take the positions and timings and velocities associated to point A and you plug them into some sort of equation, you want to get, after some finite amount of time, a path that gives you another point B. And another valid question is beginning with the point B and going backwards and finding the path that led you to point A in the first place. This is often done by means of an evolution function, a generic sort of function that maps a path in some parameter space. Granted, it does not need to be in position space. It can be in momentum or, phase space. It can be really in anything. The evolution function can actually be retrieved in a variety of ways, and the most basic of physical exercises are getting that evolution function within, for example, the Newtonian program, where by starting with the forces, you can use the masses and the accelerations to find the changes in the velocity components of particles, which ultimately yields you the associated equation of motion. So, for example, a block on a ramp, you have a mass, you have an angle, and then you find the acceleration component in each angle, and then you can find the variation in velocity. Finding the variation in velocity, then find the path through space-time. As you learn physics, you get more and more sophisticated programs. You get the Lagrangian, Hamiltonian, and even in some special cases the Nambu-Goto program, and such. The fundamental idea behind the Lagrangian and Hamiltonian programs is that there's an innate physical quantity named the action. Now, the action is this unobservable entity that is inside of every physical object. And what the importance is that if it can be seen as the fundamental quantity of motion, then we can actually distinguish different paths taken in space-time by analyzing the amount of action in joules per second that these paths take. So we have here a point A and a point B, and for example, the path A from B with 0 joules second is a different path than the ones from 5 joules second. And so each one of these paths would have a different equation of motion associated with it. The idea behind the Lagrangian and Hamiltonian then is that each is a function that will weight the path accordingly. So the Lagrangian in this particular instance is giving a particular amount of value to each step traversed in the path. So, I've expressed this with the red and blue zones. So you might think that the red zones contribute positively to the action. So they add weight to the paths that have been traversed in this region, whilst the blue regions take away weight from the paths traversing there. So you can see that the path with 3 joules second goes through a positive region for a long time, and then it has the action that it gained from this red region subtracted by the blue region. The idea then is that each Lagrangian weights the paths differently, and so to actually get all of the physics associated to a physical system in mechanics, we just need to get the different Lagrangians associated to them, and then integrate the paths along these Lagrangians to get the total amount of action. And one of the most important aspects of this formalism of Lagrangian and Hamiltonians is that you can put a field on top of spacetime, like the gravitational or electromagnetic fields. Once you put these fields on top of spacetime, all they really do is change the weight associated to each path. So in the same exact figure that I have here, you can imagine that by adding a field, you can see I have changed the blue and red regions, and so the contributions of weights to each of these individual paths is now different, and so the equations of motion associated to each path are now different. The way that we get the actual equations of motions associated to the physical path is by means of the principle of stationary action. So if you recall the previous figure over here, you can see there are hundreds of paths, but the actual physical path the particle or the object will take is only one of them. Well, how do you find the single one of them that actually is real? Now, the idea of the stationary action is that macroscopic objects will always follow a path that minimizes the variation in the action. So that means they always exist in extremes of action where the derivative vanishes. What that means is that if you were to plot the action in a graph along the path for each one of these objects, all the possible paths will have different actions. The path where the action locally is a extrema, so the derivative is 0, that's the path that you're going to take. So that often happens in the paths of least or most action, and a lot of the times it happens in the path of least action, but certain systems like optical systems do also possess paths that are taken by light as the extremas of most amount of action. And that's really expressed by this principle over here. If you vary the action infinitesimally, you're going to have to get 0. So if you take the action by means of integrating a path along the Lagrangian minus the infinitesimal variation of that path, that ought to get you to 0. Now, the fundamental idea behind the other physical quantities in physics, such as momentum and energy, which I shall call as momenergy, or the form momentum as it's usually known, is that each one of these is actually a composites to the action. So the temporal section of the action associated to a path is the energy, whilst the spatial section is the momentum. So if you take the path P over here, by projecting a shadow on the time axis of a single infinitesimal segment of that path, delta t, and multiplying that infinitesimal segment by the amount of energy the particle possesses in that infinitesimal segment, and then you sum that to the momentum times the infinitesimal segment of spatial displacement that the particle has on that path, if you add those together, you get the action, the total amount of action on the particle in that exact instant of time. And that's actually where the associated quantities come from. So you can associate momentum to space and energy to time. And that's most often made very clear with Noether theorem. So since this is just a review of everything we've learned until now, it doesn't really make sense for me to prove the Lagrange equations or Noether theorem, so I'm just going to straight to the actual process that we're interested in, which is how to visualize particles as waves, but in classical mechanics. And that's done with the Hamilton-Jacobi principle, which is also considered to be the nearest classical link to quantum mechanics. So the idea is this, right? If you think of the Lagrangian or the Hamiltonian, they associate weights to each region of spacetime. But it's actually possible to write down a mathematical function of the action that's written down in terms of differential forms. Once you do this, you get this one form over spacetime in this particular instance, where you have crests with a constant amount of action. So you can see that we start at point A, nearest to the crest of action equal to 0, and then to 1, to 3, and such to 9, until we get to point B. Now, these crests of action can actually be visualized as actual wave crests and evolve as such. Now, the evolution of these wave crests is determined by the Hamilton-Jacobi system in question and the Hamiltonian in question. But the most interesting thing is that the actual path that gives you the stationary action is the path that is followed once you follow the wavefront or the wave vector of these action crests. So if you have a particular volume of space-time and you have these crests of constant action, what you can do is this: by following all the paths that are perpendicular, all the vectors that are perpendicular to each one of these crests, you get the actual path of the particle. So you can imagine that the particle is somehow dragged along these crests of action as time progresses forward, and that gives you the evolution of the physical system in hand. Much more interesting is if you take the gradient of the associated action crests across this path, that gives you the moment energy content in the path. And that's expressed in the Hamilton-Jacobi equation. So in the left-hand side, we see the partial in respect to time to the action negative is equal to the Hamiltonian function, with the actual inputs variables into the Hamiltonian function being the position, the time, and the variation of the action with respect to space. Now, if you recall the definition that we just gave of the action being the momentum times the infinitesimal displacement in space minus the infinitesimal displacement in time times the energy, you can see this equation is not very surprising. We rephrase this statement in terms of the rate of change, the dynamic phase of the action with time. With the dynamic phase, we are really equiparing this crest of action with waves right now, with phase being the phase of the action as time progresses along. So, 0, 1, 2, and 3 are phases of the same wave progressing forward in time. That variation of phase with time is equal to the Hamiltonian being given by the rate of change of the dynamic phase of space and the space-time position of the particle. The action associated to each path can be again changed by the presence of fields of top of space-time because they change the Lagrangian weights, right? The most basic example of this is in electrodynamics. We have a two-form which represents the Faraday geometric entity, and the Faraday two-form is composed of electric and magnetic sheets. So in the little right-hand side, we see that it's a composite of multiple different two forms given by dx alpha, wedge dx beta. And to each combination of these two forms, we give an associated weight. You can imagine a contribution to the action, which is given by one component of the Faraday field. So in the left-hand side, we see F alpha beta. That's also known as the Faraday tensor. So the Faraday tensor, as we can see here, is a very simple tensor. It's composed of 6 different two forms that are associated to the electric field, and these forms exist in time and space. So you can also see them as bivectors, and the bivectors have an orientation associated to the time and the space they're in. So EX, EY, EZ. But we also have minus EX, minus EY, minus EZ because we also have the bivectors that are not T wedge X, but maybe X wedge T, which is the negative of the previous bivector. So we end up with 6 contributions of the electric field. And then we also have the same exact thing for the magnetic two forms, or the magnetic bivectors, where they are all antisymmetric in space because they possess different orientations, but we end up with exactly the same thing. So the electromagnetic field is decomposed into 2 sections. It's composed into a purely spatial section, which is the magnetic field, and a spatial temporal section, which is the electric field. And there is a general rule which mirrors that of Einstein's general relativity, which is that charges tell Faraday how to curve, and Faraday tell charges how to move, and those are the equations of motion associated to the electromagnetic field. I'll talk about this a little further on. But of course we can visualize Faraday as a regular set of two forms in this egg crate configuration. The flux tubes in both space and time extend indefinitely. Well, actually, the exception is that the electric flux tubes end in charge, but every one of these flux tubes, by virtue of being a form, also has an orientation that we may write down as a little arrow indicating a circle. So here we have two equations of motion associated to the Faraday field. We have dF equals 0, so the exterior derivative applied to F is equal to 0, or the boundary operator to F is equal to 0, which interpreted means that the electric or spatial temporal sections of Faraday always end in electric charge. And the second statement is that d Hodge dual F, or d star F, is equal to 4 pi times the electric current density J. And what this statement means is that the magnetic forms, which are all the purely spatial sections, only get distorted at charge, and this distortion is proportional to the current density at the region. So the interpretation would be, again, that the Hodge dual of F is just the egg crate structure of the flux tubes of F, but, rotated to 90 degrees, so it all gets purely spatial. The other possible statement that you can make about the second law is that the number of tubes in a volume is equal to the amount of electric charge in that volume, and conversely, the flux tubes generated are proportional to the current density. So here I have two pictures. In the left, I have the purely spatial forms are constant in time, and so they have these glowing beams to them, whilst the spatial temporal sections of time, constant time, which are the electric lines, always distort and end at the presence of electric charge, but you can see that the magnetic forms only distort around them. Of course, this is a two-dimensional drawing, so you can't see the distortion. Now, the idea is this, right? The contribution to the action that the electromagnetic field does is proportional to the integration of the path, of course, minus the mass times the space-time segment that was traversed, minus q times the vector potential times, integrated over some space-time region dxi. So why is this important? Well, because we see that the electric charge serves then as what we would call coupling constant. So this will come back to quantum field theory. The Q, the electric charge, only tells us how much action the electromagnetic field contributes to the particle path. So if you have a very large amount of electric charge, regardless of the sign, it means that all of the contributions made by the vector potential will be amplified and will then contribute to your integral. But if you are a neutral object, that means there will be zero contribution to the vector potential. And so the action you get is just the regular action, which is the mass times the space-time segment that you traversed. You can rewrite this dynamical law in terms of a more convenient fashion, which is separating the vector potential AI in two different other structures, which we will call the voltage, or the electrostatic potential, and the vector potential related to space. And so the integral now gives m gamma being the Lorentz factor, times dt, which gives you the infinitesimal path segment oriented to the future, minus the charge, of course, but now we separated the vector potential into a temporal section, which is V, the voltage, the electric potential, plus the vector potential, the magnetic potential, A, to its infinitesimal segment dr. And what's interesting about the interpretation of these with the idea of them being forms is that there's a continuity condition associated with these two equations. And so John Archibald Wheeler made a really interesting analogy, which is that you can knit fields into arbitrary configurations, and that's really what happens in real life. You have a null electromagnetic field, but by producing charges or moving charges around, you can knit the field into any desired shape or strength, because if you increase the density of a form, you also increase its strength, so ultimately you can do those procedures. And in the right drawing, we can see what's very interesting in the interpretation of the action above. If we have a electrically charged object Q, this electrically charged object will actually move about according to the amount of sheets of electric magnetic fields that it pierces. So for every temporal sheet, which is the electric field, it will actually have a contribution to its energy, whilst every magnetic sheet it pierces, which is the constant position sheets, it will have a contribution to its momentum. So the magnetic field contributes to the momentum, whilst the electric field will contribute to the total energy in this particular action. And so that's how the electromagnetic field operates. Here we can see a very rudimentary picture of how the electromagnetic field actually looks like under these discretion, which is you can write down the Faraday structure in terms of a single electric charge in the middle, and by writing it down in terms of a spherical coordinate system, you get that the Faraday field is equal to minus the charge over the radius square times the spatial temporal sheets, and the Hodge dual is the purely spatial section of the electromagnetic field, so we end up with a q sine of theta times elements of d theta d phi, which are completely completely angular components centered around the sphere. And so the electromagnetic field around a central charge can actually be seen as flux tubes extending indefinitely around the charge, and you can see that the density of the fields decreases exponentially, right? And that actually is what gives rise to the inverse square law. If you took a cross-section of this flux tube structure, you see that because the density decays exponentially, less and less sheets are pierced, and so there are less and less contributions to the action as the particle travels along in different distances across the electromagnetic field. And you can actually write down very well the Lorentz force as a contraction of the force velocity in Faraday, and so this is a general proof over here. However, we will see a far more interesting way to visualize this proof in the next slide. So here we see how we pictorially interpret what I just said in terms of the temporal sheets, or the electric sheets, contributing to the energy of the particle, and the magnetic components of the electromagnetic field contributing to the momentum. If we take a point A and take it to a point D, but we take it through two different paths given by ABD and ACD, the fundamental idea behind gauge theory, and these two paths have a different amount of action to them. So although they make a square, and so you traverse the same amount of time and same amount of distance, you actually get different amounts of action associated to each one of these paths. And so we say action is non-commutative under parallel transport, which is the transport of ABD to ACD, of a particle in a boundary region of space-time containing an electromagnetic field. And so what that means is that what happens is this. If you take the path AB to D and ACD, in this particular case, we're looking at a space-time diagram with Tx, so time and space. What ends up happening is that the difference in action between these two paths over here is given by the electric field times the area. So when you cross to A to B, that gives you a contribution of the electric field, but gives you no contribution to the magnetic field. But once you give the cross to B to D, that gives you full contributions to the magnetic field, but no contributions to the electric field, because you are traversing no time. Similarly, if you traverse AC, you have no contributions from the electric field because you are only traversing spatial sections, so you're only traversing the magnetic field. And once you cross C to D, you are only crossing temporal sections and not spatial ones, so you only get contributions from the electric field. And so what that means is that the total difference in action is the electric field. So the electric and magnetic fields can be seen as things that amplify or diminish the amount of action that you have depending on what kind of path you traverse through space-time. Similarly, if we were to switch this space-time diagram from a Tx to a YZ, we would see that because we only have purely spatial contributions, the difference in action associated to the different paths is given by the magnetic field times the area. So this is a very important thing, right? And so we can see the proofs over here. Because what that means is that we can then see through the principle of stationary action that the path or particle will take a path that's sort of in the middle of these two, right? So you can imagine a particle takes a path from A, B to D and AC to D. The path from A, B to D has a lower amount of action than the path from AC to D. But because the difference in action between the two paths actually increases only in the range where they vary between space and time, you actually get a sort of circular cross-section as being the principle of stationary action applied to the segment of a square. And this is actually the origin of the Lorentz force law. So the reason why particles make helicoidal, helical shapes through space-time and through space itself is because since you have this contribution of the action increasing in the transition from A, B to B, D, you get a quarter of a segment of a circle. And so it turns out it's reasonable to think about, because of this lack of commutativity between the actions, of fields as a piece of geometry. So in general relativity, if you want to measure the curvature of space-time, you do parallel transport around a closed path, or you compare the different curvatures between different paths, and it gives you the total amount of curvature. And you can see it's not very different here. We can see the field as a curvature of the integral vector potential, and by taking the vector potential A beta and transversing it into the direction of partial alpha and taking the difference of that of partial beta to A alpha, that gives you a level of curvature. So if that curvature is zero, there is zero electromagnetic field in the region. But if there is a non-null amount of curvature, that actually equals the amount of electromagnetic field in the region. And so what that means is that classical gauge theory states essentially that the field strength in a region is roughly proportional to the area deficit, or the curvature present in the field and the vector potential of that region of space-time. So if you have more curvature, that means you have a larger strength. If you have less curvature, you also have, a lower amount of contributions to the action, which is equal to the amount of strength of the electromagnetic field. So roughly speaking, we can put the field strength as equal to -1/4 of the curvature. And we can write this down as the Lagrangian being equal to -1/4 of the inner product between F and the dual. And of course the field strength is not the Lagrangian. The field strength comes after we integrate the particle action and so on. But I just want to try to make that idea clear, that the field strength is proportional to the curvature. Now the -1/4 over here is sort of irrelevant, right? Because if you integrate a constant, then you can just pull out the constant out of the integral. And so this is just done so that once you do the integral of the curvature, you get, you can cancel out some stuff and you get the correct equations of motion for density, electromagnetic, that sort of thing. It's just a normalization factor. But anyways, you can see this Lagrangian as in terms of Riemann curvature. So the Lagrangian weight that the action is given is actually just a torsionless Riemann curvature tensor. And torsionless is really interesting, right? Because although it's anti-commutative in the sense that it has curvature, it's not non-abelian. So this is what we would call an abelian gauge field. Now the reason for this is that if you do a closed path and you increase the amount of curvature, the path will actually always be closed. There will never be anything that opens up the path that you just traverse, which we call torsion. And this is actually very important because that's related to what we call the boundary of the boundary. So one of the most important geometric principles, and perhaps the most important geometric principle in gauge theory, is the idea that the boundary of a boundary is zero, right? So if you take two boundary operators and apply it to the vector potential A, that gets you to zero. The fact that the boundary of a boundary is zero it's made more explicit in the book Gravitation, where you can actually equate this idea of the boundary to the automatic conservation of charge and the automatic conservation of electromagnetic fields. And so it becomes a dynamic necessity in the sense that you need the fact that the boundary of the vector potential to be zero in order to actually not break things like the conservation of charge and current density and such. Now, it's very interesting that we didn't see the totality of what we talked about until now, which is that the fields are seen as curvature. The action is just seen as a weight that's given by the Lagrangian to each individual path. The particles as waves, because we can see the motion of particles in terms of wavefronts with the Hamilton-Jacobi equation, and so we can see the totality of physics as geometry. So the Faraday tensor can really be seen as the curvature around some rectangles of legs given by the basis vectors alpha and beta, plus the sum of the boundary of the vector potential. Now we've seen that the boundary of the boundary is zero, so this term vanishes, and so we really only need to care about the curvature. Now, I want you to keep this in mind because in non-abelian gauge theories and quantum field theory, you will see later that the boundary of the boundary does not vanish. And so that actually gives you a torsion term which corresponds to color charges. Anyways, the field is then weighted as a Lagrangian function. And we can see the Q squared, the electric charge square, over there acting as a coupling constant, right? So, if there's zero charge, that really destroys the whole thing. It gives you no contribution to the action whatsoever. But if you do have charge, then you increase or decrease the integration constant. Now the actions turn to a dispersion relation, right? So when you talk about wavefronts, when you talk about wave mechanics, you're talking about dispersions. The wave disperses more quickly or disperses slowly, those sorts of things. And this coefficients of dispersion are given then by the associated fields on top and so on, the Lagrangian and the Hamiltonian function. So once you do that, once you turn the action to a dispersion relationship, that gives you the following Hamilton-Jacobi equation. And you can see that on the left side, in the same way that we were talking about the variation of the dynamic phase with time, which is equivalent to the energy, that equals the density of the Hamiltonian, the density of the energy of the electromagnetic field. And similarly, inside of these terms, you can see that we also have the Hamiltonian as a function of the momenta, which then gives us the density of electromagnetic momentum canonically conjugate to A. And what we happen to write that as is actually just a multiple of the electric field, but you can see this squiggly electric field over here. That's just to indicate that its contributions of the electric field to space, right? But that's really irrelevant. You just need to think of it that the contributions to the momentum associated to a particle wavefront is given then by a multiple of what we would give by the time dispersion of the wavefront. And then we have the magnetic field over here as well, and the more you increase it, the larger the variation of the action. And so there's actually a very useful chart of using this sort of formalism to talk about different ways of visualizing the electromagnetic field. So if you, instead of writing the electromagnetic field in terms of the Faraday tensor, you can actually write it down in terms of things like the scalar potential phi and purely the vector potential. And that gives you a different representation of the electromagnetic field in three-dimensional space. And this, representation is more wieldly because in certain scenarios, because it gives you also the macroscopic fields. So the dual rotates around and gives you the different forms associated to each one of these, so you can actually do computations. This is much more clearly explained and explored in the paper linked below, which introduces this sort of representation, but I just think it's neat. We can talk about gauge invariance. So the electromagnetic field can be written down, if you want to, as a sum of two bivectors, a complex bivectors, or if you want, it can be written down very commonly in terms of sums of complex forms. Now, if you use the formalism of space-time algebra and geometric algebra, you can write down a picture of the electromagnetic field in these terms over here. So you have the magnetic field B is given as terms of wedges of the basis bivectors of space, whilst the electric field is the basis bivectors associated to time and space. And the sum of the two is given by the the regular bivector addition rule, which gives you the total Faraday field. So you can see that the magnetic field is a bivector field and the electric field is a bivector field. Is just exactly the same thing as seeing it as two forms. It's not really relevant. One of the interesting aspects of it, however, is that the presence of the pseudoscalar, which mimics the presence of the complex numbers, immediately leads us to a very handy representation. You see, if you can imagine the electromagnetic field as being a complex number, we can actually color each point in space-time where each bivector of the electromagnetic field is to a color associated to the phase of that complex number, right? So in the same way that we can write complex phases as in colors of regular numbers, we can do the same for bivectors. And so we would have this very colorful function in space-time. And the idea of U1 gauge invariance as being the gauge invariance of the electromagnetic field is that if you take any one of these bivectors and you rotate them by some angle theta globally, that actually doesn't change the physics at all. And this is made explicit by taking derivatives of the vector potential in relationship to space-time coordinates, and that gives you no variation to the action. And so we can see that that's how U1 comes about as the classical gauge invariance, because U1, the unitary group of transformations, is just a group of the circle. It's just a group of everything that's invariant under an angle change like this, and the complex numbers are the same. And so it turns out that if you, again, think of the electromagnetic field as this complex bivector, then if you do a phase transformation in it, it doesn't change value. And so that's very good. That's how it works.